Okay. Now, has anyone's okay? So most people have finished the quiz. So everything's fine with that. But as for the regular homework, that is not due for another week. Has anyone actually started that?
Well, did I? Yeah, did I read the right spot? Is it these problems from your textbook?
Right.
Okay, so write them out loud, carry out this.
Yes.
Gaussian, MATLAB,
That's those.
bandwidth.
Yes.
Okay.
Yeah.
I just wanted to make sure. I did this much.
Okay.
Have my problem.
I don't suppose that.
You were working on this LQT composition. Yeah.
Okay.
Sorry.
I don't suppose anyone has any questions about them.
No.
All right. Well, I didn't really expect anyone to anyway. In fact, I expected most people had not even started yet. Because, it is a whole week until they're due.
Some of us have time issues.
Yeah.
We ought to be on it.
Yeah. However, it would be a good idea if you bring your questions on Wednesday. So, like for instance, if you're not sure what you're even supposed to do, like what's the question asking for, and yeah. Now the thing is on with it being due on Monday, certainly we can talk about it Monday also, from last minute questions and so forth. Because then I wouldn't care if you didn't turn it in until that night. Well, actually, most of you know how I am about due dates, so.
So since it's optional, and you're saying turn it in, do you want everybody to submit something, or are you going to give us feedback strictly, or how are you planning on?
Okay. What I would like you to do is, if you choose to do this assignment,
which I think is most of it.
Then I'm happy to give feedback on it to everyone turns it in. But I want you to tell me when you turn it in if you want me to include this in your grade or not. And because if you want to do it just for the feedback, and I can see how, especially some of you who took 561 last semester might be in that boat. That's fine, and I'll still grade it just like everybody else is. But just let me know what you want to do. So, yeah.
I do have a question about, not specifically about a problem, but for example, what is complexity of Gaussian elimination?
Yeah.
Do you just want the O with parentheses and what it is? I don't want to say that out loud.
That's the answer.
So I don't have to say the complexity of Gaussian. Do I have to write complete sentences? How do you? Do I have to say the complexity of Gaussian elimination is this? I mean, how are you about that?
As direct as possible.
Yes.
Okay. Okay.
Yeah.
I just haven't had you before, so I want to make sure.
Yeah.
What you want.
I'm not looking to read an essay.
Okay.
Yeah.
Got it.
So, and
people on, but.
That reminds me, when I was undergrad, I took a class that's, I guess it's similar to USM's 417, 517, is on PDEs. And so it was a class mostly grad students, and I think I might have been like the lone undergrad, whereas I guess here it tends to be more flipped to mostly undergrad. But so what I found was that grad students typically, when they do their homework, they write a book. And it's also amusing to see students transition from undergrad to grad that also start writing their homework and turning in a book. And I didn't, because I was an undergrad at the time. So I fit the whole assignment onto one sheet. And they just found that so strange. So I went up and put it on a table to turn it in. So when they go and they're turning their books in, and they're looking at mine, and I see them. They pick up my paper, looking at it. How did you do that? Like, well, I didn't feel like writing a whole lot. It doesn't mean it's wrong. So, but yeah, it's. I will say this, that when I am grading, I do. And this is, I guess, largely directed at those of you who have been grad students, like not the rookies, but from 773 and last semester and 561. No, I do not read everything. There are certain key things I'm looking for because grading is my least favorite part of a job, and I've learned to be very fast at it. So, well, yeah. Because I basically want to try to get the point total right, and I'm sure there may be some eloquent mathematical prose that I'm missing, but I've come to terms with that. Okay, so don't kill too many trees. Actually, speaking of which, for first submission, again, some of you are familiar with this from last semester, but what I prefer is just email it to me. Scans of your pages, because what I've found, unfortunately, I don't.
You don't file nothing.
I don't take many assignments on paper anymore, and the few times that I have, I've lost them or had to find them. So I don't want to put a student in that situation. So if it's in my email, there's no chance of losing it because I don't delete anything ever. Preferably if you just zip everything up. So basically, there's just like one attachment, and I can work with it from there. Because basically, I just take all your pages and I just open them in preview and just look through them, or I can grade it on my phone. So it's quite nice. Okay. Now, so today we're starting a new chapter. So, a new problem to talk about. So this is chapter 6 in the notes. In my book, it's chapter 4. Okay. Remember when I was freshman taking a physics class, and so in the lab, we're saying for reporting your results and whatever, plotting your data, you can put in a least squares line. I'm like, what is that? I never heard of that. And they did bother explain that we're all supposed to know. So I felt really dumb at that point. I didn't learn what it was until my first statistics class. So a problem of if you have a bunch of x, y values in the plane, how do you find the line that best fits all of those points in some sense? So that is an example of the kind of problem that we're going to be looking at here. So to introduce that problem a little more formally, so an application of this. Suppose you're given a set of observations, points in the plane. x1, y1, x2, y2. And let's suppose you have m observations altogether. For example, let's suppose that the x's refer to time and the y's refer to temperature. Anything like that, where you have a relationship between whatever independent variable x and dependent variable y. So to find a function f of x, which has, and what you're doing is you're prescribing that the function has a certain form. So you're saying that your function f is a linear combination of certain functions that you're specifying. For example, polynomials. Maybe these functions are 1, x, x squared, etc. Maybe they're sines and cosines, something like that. And the coefficients are unknown. So you want to find, so these are prescribed, and you might determine them based on what kind of relationship you think you might have. Like suppose you plotted this data, and you think that there's a roughly linear relationship between the x's and the y's. Then that you might take that into account. And maybe you choose one function to be a constant function, and the other to be x. So what's a combination of those functions that best fits the data? So you want to find a function f of x. That in some sense best fits these observations. So what you're doing is you're really setting up a system of linear equations. So you might have like C1 phi1 of x1 plus C2 phi2 of x1 and so forth up to Cn phi(n) of x1. So everything has x1 plugged into it. And when you plug in x1, you're supposed to get y1. And then you keep going. So now you plug in x2 throughout. Let me get lazy here. Cn phi(n) of x2 must equal y2, and so on until the very end. You plug in xm, which equals ym. So you have, oh, that's annoying. Thank you.
It's supposed to be V1 from the second one.
Yeah. Good catch. Yeah, I screwed up the coefficient and caught that, then missed the function. Okay, so now you have m linear equations with the n unknowns, C1, C2 up to Cn. So you can express this as in matrix vector form, like that. So you have a matrix phi, which is m by n. C is n by 1 as the coefficients, and then the y values from your observations, m vector. So Pij is the function phi j evaluated at xi. All right. Now, but I haven't. Now I need to talk about values of m and n. You know, how many observations we have, as opposed to how many functions we're using to describe them. So, so these functions, phi1, phi2, up to phi(n), should be linearly independent. So in other words, it should not be possible to express one function, any one of these functions, as a linear combination of the others. For instance, you're not going to have x and 2x among them. That's totally redundant. So for instance, if two functions are scalar multiples of each other, you would not include both of them. So and you need that in order to ensure that if there's a solution at all, that it's a unique solution. We want to have one best fit. Okay. So as long as your functions are linearly independent, that's perfectly fine. But the only way that could be assured is since you're actually plugging in all of these points into these functions, you should at least have m be greater than or equal to n, because if you're only observing at a few points and you have many functions, that's going to be a system that is called underdetermined. There's no way you could have a unique solution to that. Now, so that's one. So we're not going to talk about a situation where m is strictly less than n. That is another kind of least squares problem. It actually is covered in the notes in the book. I'm just not covering it in this course. I may say something about it, a little something about it later, but because it is an interesting problem, it's just not where I want the focus to be. Now, let's suppose that m is equal to n. So the matrix phi is square. We know how to solve that problem. We can use Gaussian elimination. So, in other words, all the chapter 3 stuff that we've just been covering about. So I'm not really going to talk about that case either. So the case of interest to us is m is strictly greater than n. So then the system is called overdetermined. You have more equations than you do variables. So, so the solution might not exist. And the problem is still very much worth solving because data that you're gathering you're not necessarily going to have precise relationships among your variables anyway, simply because of measurement error. Like, for example, suppose it looks like y depends roughly linearly on x. So then, in that case, you may have a zillion observations, but n, the number of functions you have, is only going to be 2. Because you can have you're doing like y equals mx plus b, so you have your constant function and a linear function. That can still accurately capture, at least as reasonably accurate as you can expect, relationship between x and y. You may not want a function more complicated than that. Because really you're trying to find the simplest relationship between the variables that describes what's going on. And it's not the sort of thing where you necessarily expect high accuracy. Okay, so let's talk about when does a solution exist? So now you switch back to my regular notation. When does ax equals b? Well, actually, not the unique solution. When does it have a solution at all? So now we're talking about existence rather than uniqueness. And it's very easy to describe the answer. Solution exists if and only if the vector b is an element of the range of A. So what you're doing is you're taking your x, you're plugging it into a function that computes A times x, and then the output of that's supposed to be B. So, so the range of A is a set of all linear combinations of the columns of A. So if you can combine the columns linearly to get B, then B is in the range of A. Okay, so a simple example. Let's suppose A is this matrix. So I'm just taking the first 2 columns of identity. And let's suppose that B is this vector. Well, B can definitely be expressed as a linear combination of the columns of A. So AX equals B has a solution, 1, 1, because if you could take the two columns, because what you're doing is AX is taking a linear combination of the columns of A. How you're combining them are the elements of X. So what I'm doing here is I'm taking the two columns of A and I'm just adding them, and I get B. On the other hand, let's suppose B is this vector. No solution. There's absolutely no way you can combine, take linear combinations of these columns of A and have any hope of getting B because of that 1 down there. If this was 0, then there would definitely be a solution. So this is a case that's of interest. That you're trying to solve AX equals B, where now it's no longer a square system. A is a rectangular matrix. It's tall and thin, so more rows and columns. And the case where B is not necessarily in the range of A, so we have no assurance of existence of a solution, let alone uniqueness. So what do we do in that case? Since we cannot solve a system exactly, our goal is to solve it as closely as possible. And we need to figure out what that might mean. Oops. Okay. Oh, dang glare zone. Oh, wait. I think the camera, when I'm standing here, I can't really see it.
There you go. Keep going. Now go up.
Okay. Well, not that I'm going to use this room probably. With my board usage, you never know.
That's true.
And you would know this. Okay.
Don't kill the table.
All right. Okay, so so the goal instead is since AX equals B is impossible to solve exactly, we want to minimize the difference between AX and B. So this vector, B minus AX, which I'm going to label as R for residual. Well, I introduced residual last time when I was talking about the condition number. So this is quite a useful vector here. So we want to make the residual as small as possible. And here I'm using a vector norm. So we're taking the magnitude of this vector. We want to minimize that magnitude. But that still doesn't help us because, as I mentioned last time, there are several notions of magnitude. There are all these different vector norms, the P norms, 1 norm, 2 norm, infinity norm. Which one do we use? Which one leads us to a systematic way of solving this problem? Which norm do we use? And a good choice is, so if I use a P norm here, that's also the only vector norms I talked about, P equals 2. In other words, I want to minimize this 2 norm, which is the square root of the sum of squares of these differences between each component of B and each component of AX. That should be the sum from 1 to M. Okay. All right. Now, why the 2 norm? Because if anything, the other norms that we've seen are simpler. Like a 1 norm is just the sum of the absolute values instead of sum of squares. The infinity norm is just the largest element. Why use this norm? And the reason is the 2 norm is a differentiable function. All right. If you're taking a 2 norm of a vector that has however many components, it's a differentiable function of its components. Why do we care about being able to take a derivative? Why does that help us? What were you told in calculus that derivatives are used for? Yes, the slope of a tangent line, but what else? Applications of a derivative. What did you say? I didn't catch it.
Say it again, Carly. Do it.
No one else said anything right, so. Oh, I see. Oh, yeah, which is equivalent to what he said, rate of change. So. Okay, that's like the meaning of a derivative. But what kind of problem, like in Cal 1?
Are you talking about where you can find the area under a straight line with regular pre-calculus, but when you use calculus, you can find areas under slopes and curves and things like that in application?
Well, it's just more about integration. But yeah, like application problems. So what's an application problem involving a derivative?
Like rate of change. Yeah, that's where immediately where I'm going. Rate of change.
Okay.
Hold on. Give us about 30 minutes to think about that.
Okay, I'm not going to give it away yet. Let's see if I can
say that again.
I'll see if I can use power suggestion here. There's a certain kind of problem that you had to solve often in Cal 1, and when your instructor problem
trig functions.
No. What I told you to do was using these exact words: take a derivative, set it equal to 0.
Your critical points,
which are useful for finding
the max and min. Yeah.
Yeah, we're trying to find a minimum.
Minimize.
Yes.
Yeah, that would have taken about 30 minutes.
Yeah. Okay. Longer than 30 minutes.
There's something on the board. Impossible. Yes, I agree.
Yeah. Okay. That's impossible. Okay. So that we can find a minimum of this. So what I'm going to do to describe this, how we're going to use calculus, multivariable calculus, to solve this problem, I'm going to do a quick review of certain aspects of minimization, first in one dimension, because you remember that from Cal 1, and then what we do in multivariable calc, which, well, let's see, I think there are, 2 people in this room took multivariable calc from me. So they would have gotten full coverage, but the rest of you not. Okay.
You looked at me. I'm taking it. I'm one of those 2.
I would think you would remember. It was a while ago, I know. Okay. All right. Whoops.
It's okay.
Okay. All right. So for minimization, so in the 1D case, so y is equal to f of x. So you have a local minimum at some point I'll call x star if f prime of x star is 0, so derivative is 0 at that point. And what about the second derivative?
Inflection.
Sorry, what? Right. So what do we? If you want the first derivative to be 0 at the local minimum, what has to be true of the second derivative at the local minimum? Yes. Concave up. Okay. Now, And I'll call it Taylor expansion. If I expand around the minimum, x star, to be that plus f prime, x star times x minus x star, plus 1/2 f double prime, x star, x minus x star squared, plus other terms. But I'm going to cross that out. Those other terms will be 0 if f is a quadratic function, because then the third derivative and everything after that would be 0. And I mentioned that because the function we're going to be minimizing is a quadratic function. So it's really only, these are the only terms we care about. So, well, the derivative, first derivative is 0. So we wouldn't have this term. And then the second derivative at this point is positive. So this term is always going to be positive unless x equals x star. So what we have is f at any point is f at x star plus something that is at least non-negative. So that tells us that f of x is greater or equal to f of x star. Also, we can say that f of x is strictly greater than f of x star. And that's true for any x along the whole real line, because this term is always going to be positive if x is not equal to x star. So that means we have a x star is a unique, not just a local min, but a global minimizer. So these quadratic functions are quite nice because, well, think of it this way. You know, looking at the graph, a parabola that's facing up, unique minimum. Whereas if it's facing down, it has a unique maximum. So that's what we have for a quadratic function of one variable. Here we have a quadratic function of several variables for dealing with ax equals b. But I want to review this because now I'm going to take this and generalize it to the case of higher dimensions. So minimizing a quadratic function of several variables. Okay. All right. So in the n-dimensional case, so you have y, the vector y is a function of n vector x. So, so f maps Rn into Rn. Now, same idea, but everything has different terminology in a multivariable case. So we have the gradient. Wait a minute. No, sorry, I goofed. Y is not a vector, y is a number. Okay, so it's not a vector value function. Okay. Oh, come on.
It's the only thing that I have written on the page.
You taking notes in pen?
Always.
Oh, okay.
It's only when you make a mistake that it messes me up.
Like, God, I feel like I just killed a tree or something. Jeez.
It's okay.
All right.
I'll plant one later.
Okay. I feel better.
I'm like the queen of
Okay. So the gradient of f is a vector partial of f with respect to x1, x2, and so forth. Okay. And then we have the Hessian, which I'll use H subscript F. That is a symmetric matrix where we have all the second partial derivatives with respect to all possibilities of all combinations of variables. Like I said, we need more room here. So including the mixed partial derivatives, which makes it an n by n matrix. And because mixed partial derivatives are equal under our assumptions about f, that's why matrix is symmetric. Okay, so that is the Hessian of f. So that's how first and second derivative generalize to higher dimensions. Okay, so when do we have a local minimum? At a certain point, which I'll again call x star. Similar to what we have here. We have the gradient at that point must be the zero vector. All of those partial derivatives must be zero. And then the Hessian at that point now, the second derivative over here, we need it to be positive. Here we have a matrix. So what do you think needs to be true about how do we generalize that criteria? A number being positive to a matrix being what? What? Yes. So we already have it as symmetric. So SPD, symmetric, positive, definite. And the thing is, in calculus textbooks, they give you a condition for partial derivatives, and they never tell you that really looking for the Hessian to be symmetric, positive, definite, because that's a linear algebra term, and it'll blow the students' minds. And the thing is, whenever I teach Cal 4, it's like, well, if you allow linear algebra, it's really easy to see how everything you learn in one dimension carries over to n dimensions. And talk about it anyway, in case students who know some linear algebra might appreciate it. Everybody else is like, ugh. So, but that's why this kind of linear algebra is important, because it helps people see connections between things and hopefully understand them better. Now, and you also have, for Taylor series, it's similar. So f at whatever x is f of x star plus, so here, for first derivative term, it's the gradient times the vector x minus x star. Now, note that I wrote the gradient as a row vector. This is a column vector. So what we have here, this is a dot product. But at this point, the gradient's 0 anyway, so the whole thing's going to be 0. And then, for the last term, we have x minus x star transpose Hessian at that point times x minus x star again. X minus x star. And you may recall from the definition of a symmetric positive definite matrix, a vector transpose a symmetric positive definite matrix times that same vector must be strictly positive as long as the vector involved is non-zero. This kind of expression, vector transpose matrix times same vector, so like x transpose ax, what did I call that back when I introduced it? What kind of expression was that? Yes, you can look back in your notes. Anytime you have an expression like x transpose ax, so vector transpose matrix times same vector. No.
Quadratic form.
Yes, quadratic form. So we see any quadratic function, like I'm assuming f is, can be described in terms of a quadratic form plus these lower degree terms. Okay. So same idea. If x star is where the minimum is, then f at any other point is equal to f of x star plus 0 plus something that's definitely positive. So again, see, so x star is, again, the unique global minimizer. Okay. So now what I'm going to do is apply this, gradient being 0, Hessian being symmetric positive definite, to the function that I want to minimize for approximately solving. So for that case, we can actually compute the gradient and Hessian and make sure those conditions are satisfied. So for numerically algebra class, we're doing an awful lot of calculus. Okay. So a function in this case, okay, 1/2. All right, so now before I said I'm going to minimize the 2 norm of b minus ax, but now I have a slightly different function here, 1/2 that norm squared. Now why did I do that? Really it's just for convenience. Because if I minimize b minus ax, I'm also going to minimize this, and vice versa. Because I'm squaring it, so I don't have to deal with annoying square roots. That complicates the differentiation. The 1/2 is sitting here because when I take a derivative, I'm going to get a factor of 2, and this will cancel it out. So it's not essential by any means. It's just makes for a cleaner presentation. Okay, so the question is, what is the gradient and the Hessian? How can we make sure that the gradient is 0? How can we make sure that the Hessian is symmetric positive definite? Okay, so first I'm going to write it in a different form to help with that. So, because when you take the 2 norm of a vector squared, that is the same as taking the dot product with itself. So these two are exactly the same. But written this way, I can take a derivative. Okay. Now, so to get to that point, though, I'm going to expand this. So basically, you're kind of foiling it out. So what I have is B transpose B minus, now remember, the transpose of a product is a product of a transposes in reverse order. So this is going to be X transpose A transpose B minus B transpose AX plus X transpose A transpose AX. Okay. Now, before I go any further, I can simplify this a little bit, because what we have here, this is the same as AX transpose B. Well, here we have AX dot product with B. Here we have B dot product AX. These are the same dot products. When you're taking a dot product of real vectors, which we're assuming here, the dot product is commutative. So in fact, these terms are the same. I can combine them. So I have B transpose B minus 2 B transpose AX plus the rest. Okay. Now, the next thing I can do is write these out in terms of components. So this is a dot product of a vector of itself. So it's just the sum of the squares of the components. This next one, also a dot product. So I have BI times AX, the ith component. And then this right here is also a, well, this is a quadratic form, and I wrote out a formula for that before. So it would be A transpose A, the ij entry, xi, xj. So this is based on a formula I wrote out, this would have been last Monday, for quadratic forms. Okay. Before I can take derivatives, I need to go one step further, because I like to involve just the components of x by themselves. I don't have it here. I still have the whole vector x. I need to write this out in terms of a formula for matrix vector multiplication. Yes, this is only going to get uglier. So, but you're faster than this. It's okay. All right. Okay, so I have 2 sum I equals 1 to m, and then for writing out that product, that's going to be a sum j equals 1 to n a I j xj. Okay. And then I have the rest of it. And keep in mind that A is m by n. So that means that A transpose A is n by n. Okay. So now I have a function written out. Everything's component by component. So now what I can do is to take the gradient of f, I need to take the partial derivative with respect to each component xk. So I'm just picking some arbitrary other index I haven't used yet. So I just show you what a generic partial derivative looks like. Then we can see what the gradient as a whole looks like. So I'll differentiate this with respect to xk, keeping in mind that here we have all the different x's. Okay, now, so for that, I'm going to use the fact that the partial derivative of xi with respect to xk. All right, so I have n independent variables, all the components of x. I'm differentiating with respect to one of them. Well, what would that derivative be? If I differentiate, like for example, suppose I have x, y, z. And I'm differentiating x, y, and z with respect to all of them with respect to x. What will I get? Like derivative of x with respect to x. And derivative of y with respect to x. But y, in this case, is independent of x. 0. Yeah, so this is equal to 1 if I is equal to k, and 0 otherwise. These are all independent variables. Now I'm going to use a notation, a shorthand, which I'll actually use frequently in this class, to write these more compactly. Delta I k. So this is called the Kronecker delta. Kronecker's name comes up with a lot of things in linear algebra. And this is one of them. So it's a convenient way to express some entity that is equal to either 0 or 1, usually 0, but except under a certain condition. So in this case, the indices I and k being equal. So for example, it's an easy way to describe the elements of the identity matrix. The identity matrix, all the elements are 0, except on the main diagonal where the indices are equal. So this will help me with a differentiation. So derivative with respect to xk will have a 1/2. Now, first part's refreshingly easy. This doesn't depend on x at all, so we get 0. So let's move to the next part. We have sum. Okay, these are constants, the b's. And then we get in here. So now I'm going to take the derivative. Now aij, also a constant. So I'm just going to write that out too. Until we get to here. So the derivative of xj with respect to xk is delta kj. So that takes care of that part. So it's a linear function of the x's, so the gradient is going to be, of that part, is going to be a constant. And then we move to this, the quadratic part. Well, the derivative of a quadratic function is a, what kind of function? Linear. So that's what we're going to expect from this. Okay, so I have a sum, our sum, A transpose A, ij entry, so that part doesn't change. But now we have xi times xj, and that's kind of a pain because they're multiplied. So we got to use what differentiation rule? Product rule. So we have xi delta jk plus plus delta ik times xj. Okay. All right. Now, this is rather unsatisfying because this is still such a mess. But yeah. But now we're in a position to start simplifying. Because, okay, so what we get here is, well, first, 1/2 will cancel, so we have minus the sum of bi. So what happens here is, this part will be equal to 0 unless j is equal to k. Now j is assuming all values from 1 to n, but only the term corresponding to k will still be here. So that means we're going to have a I k. So this sum collapses to that. And then we're going to have the same kind of thing over here. So I'm going to break it up into two sums, or two sets of sums for convenience. Well, okay. First part, j must equal k. So what I'm going to do is I'm going to plug in j equal k. So I'm going to have a single sum. I'm going to have A transpose A ik xi. That covers this part. And then from the other part, I must equal k. So I substitute I equal k. So the sum over I goes away, the sum over j remains. So I have A transpose A, kj, xj. Oh, and I have 1/2 times all of that. So it's not as ugly as it was. Now, I want to point out something I did earlier. Because this right here is AX component I. And when I went from that to this, I used a formula for matrix vector multiplication. So whatever I have here, the I goes down here as a row index. Then I have a sum over j. The j is a column index, and it's also the index of the vector. So now what I'm asking you to do is try to go backwards with that process. What we have here, here, here are elements of matrix vector products. And the goal is to see, well, what's the matrix vector product? What is the matrix involved? What is the vector? So I'm going to start with what you think it is. This one. This is one, of all the three, this is one that's easiest to recognize as a matrix vector product. Why? Because you have a sum over j, and you have j here as a column index, and also index of a vector. So if I were to write this as a matrix vector product, and which element of it, I'm challenging you guys to tell me what to put here, here, and here. So I need a matrix, a vector, and an index. So basically undoing what I did here. What? Okay.
AXJ.
Close. Well, the x is actually only the x is correct. What?
A transpose A.
A transpose A. A transpose A is a matrix.
K.
Yes. A transpose A times x component k. This index, the one that's not in the summation, goes here. Whatever you have here is a matrix, and then whatever you have here is a vector. So yeah, it's a kth component of A transpose A times x. Okay. Now, can anyone tell me why it's not so easy? Okay, not as easy. It's all relative.
Because that one's dealing with a row instead of column.
Yeah, the index that's being summed is the wrong one.
Question now.
What?
I didn't let you finish the
Okay,
question.
that's okay. Yeah, but you're pointing out why it's not so straightforward. So it's like, yeah, the indices are in the wrong order. We want the summation to be over the second index, not the first. How do we fix that? How do we get around that so we can still express this as a matrix vector product of some kind? Yes, we use a transpose. Because this is the same as taking a transpose, and now it's ki, which works beautifully. So that's A transpose A transpose x, element k again. But if we look at A transpose A transpose of a product is a product of a transpose, is in reverse order. Got that? So that's A transpose, which is A. It's symmetric. A transpose A is a symmetric matrix. So I don't need this here. So in fact, both of these, even though these expressions look very different, are actually exactly the same. A transpose AX, A transpose AX. So we have two of these in here, but times 1/2. So I can fill that in. A transpose A X, element K. And then the last thing we have.
Do we need to have it in that second, the parentheses, because we didn't do the parentheses for the first one? Like the matrix doesn't need to be in its own parentheses.
Oh, it doesn't have to be because
Okay.
of associativity. Okay, what about this? We want to express that also as a matrix vector product.
This is that.
Not quite. Well, certainly the vector involved is going to be B. Take a stab. Yes. A transpose B. Element. No. Okay. If one is not being summed. Yeah. It's like here, AXI. Okay. All right. So now we have an expression for a partial derivative of f with respect to xk. And notice it's the kth element of this expression. So now that makes it easy to write down the whole gradient as a vector. The gradient of f at whatever x is A transpose AX minus A transpose B. And we want that to be 0. So we must solve this system of equations. A transpose A X is equal to A transpose B. Just setting this equal to 0 and rearranging. That we have this to solve. And these are called the normal equations. So, now the thing is, this matrix is n by n, and keep in mind n is less than m. Also, I should have stated this at the beginning, assumption I'm making, because I called this the full rank least squares problem. In other words, rank A is equal to n. Another way of saying this is the columns of A are linearly independent. Okay. So that actually ensures a unique solution. So that means that AX is equal to 0 if and only if X itself is equal to 0. So, what that tells me is, if I look at X transpose, A transpose A X, this quadratic form that we saw earlier in the original F. Well, based on properties of transpose, that's AX transpose AX. But that, a dot product of a vector of itself is its vector 2 norm squared. So, if X is non-zero, this vector is non-zero. Therefore, the norm is positive. But now what I'm saying is, this expression, this quadratic form, is positive. So what does that say about the matrix A transpose A? What property does it have? What kind of a matrix is it? We know it's symmetric, because I showed that earlier, but positive definite. So this is SPD. Now, a symmetric positive definite matrix, among many other things, is invertible. So that tells me that the normal equations have a unique solution. All right, so AX equals B is not guaranteed to have any solution at all. But if I solve the normal equations instead, then I have a vector x that hopefully makes AX, B minus AX as small as possible. But there's one thing I have not addressed yet. This tells me that I have a critical point, one and only critical point. I don't know if that's a minimum or a maximum yet. In order to be sure it's a minimum, I need to know that the Hessian of my function f is SPD. Well, what's the Hessian? Now, that would require, to show you in full, a differentiation exercise like this. I have to take partial derivatives of this to get the second partial derivatives of f. I'm not going to do that because I've already taken up most of the class time. But if you really want to try it, test your understanding, you can do that. But I'll just give away the punchline here. The Hessian of f. Now, keep in mind, there's a symmetric matrix. It actually turns out to be A transpose A. And the way you can see that without going through all the actual differentiation like I did earlier, if we look here at the gradient, you're taking the partial derivatives of its components with respect to all the x's. Well, this has no x in it. So that's going to give you 0. The only thing that's left is this. Now, if we scale back to one variable, it's like taking a derivative of a constant times x. Well, it's a derivative of a constant. So this is your constant in this case. It's just dA. That's a linear function of x. Derivative of a linear function is a constant. So it's just dA transpose A. So that is how we know that we have a unique global minimum. And that minimum occurs at the solution of the normal equations.
This might be silly, but what's the difference between global and absolute?
In this setting of max and min, they mean the same thing. Yeah, because it's applying to the entire domain. I guess one possible shade of difference is that global is thought to mean like on the entire space, whereas if you're talking about absolute maximum, you might be talking about a restricted domain. But otherwise, okay. So now I've given you a way to solve the full rank least squares problem. You're trying to minimize b minus ax. So you set up this system of equations and solve it. It's done. So you think, oh, well, how come we're going to spend so much more time on this? Because that approach is actually not necessarily good. That's basically what I do this whole semester. I present a problem. Here's how you solve it. And I tell you why that method is awful. And then present another one. And this is no different. But first, to solve this, keeping in mind that A transpose A is a symmetric positive definite matrix, what approach from what I've been covering these last 2 weeks, what approach should be used to solve it? Qr factorization. Or LDLT, that's not one. Okay. Yeah, you would not use plain old Gaussian elimination because that's twice as expensive. Okay. Now, here's the but. And I'm not going to prove it here. Certain tidbits of a proof are in the homework for Chapter 4, which I've not posted yet. I picked out the problems. I will post them soon, but they won't be due for quite a while. The problem is the condition number of A transpose A. Now, I'm going to be kind of sloppy here, just because I'm lazy. It doesn't really make sense to talk about the condition number of a matrix if a matrix is not. There is a way to define it, but I won't really be able to say until we get to the singular value decomposition. But I still need to make my point, and that is the condition number of A transpose A is this condition number of A squared. And this is something that can be rigorously proven, that's sketched out in some of the problems I've signed, for a case where A is squared invertible, where we know what the condition number is. Otherwise we'd have to modify this in terms of like the pseudo-inverse. Yes?
What is the two subscript represent?
I'll write that down. The subscript indicates which norm you are using to define, because every norm induces a different condition number. So a result like this may not hold for other norms, but it does for this one. So the point is, the normal equations are a much more sensitive problem to changes in the data compared to the original problem of solving AX equals B. So that's one reason why people don't like to use the normal equations, because of this terrible conditioning. So the columns of A, they're linearly independent, we're assuming that. But if they're almost linearly dependent, then this would be way out of hand. So that's a compelling reason not to use it. Now, in the last 13 minutes, I will present an alternative. So alternative to this is called the Qr Factorization. So I'll write out what it is. A, which is m by n, is equal to QR. Q is m by m, so it's a square matrix. R has the same size as A. But I can decompose them this way. So Q breaks down into Q1 and Q2. This has n columns, and the rest go in here. So Q1 is also the same size as A. And then R breaks down into a matrix R1, which is n by n square. And then we have zeros down below. So I can actually write out A two ways, as QR. It's also equal to Q1 times R1. So that's m by n by n. Now, I need to tell you what properties the matrices Q and R have that make us want to use this. So Q is an orthogonal matrix, which means that Q transpose Q is identity. A key property is that as an orthogonal matrix, if I take a vector x and I multiply it by Q, and I compute the vector 2 norm squared, so that would be QX transpose QX. But if I write out what that is using the properties of a transpose, that's X transpose Q transpose QX. But Q transpose Q is identity. So now I have x transpose x. But again, dot product of a vector of itself is 2 norms squared. So notice the norm of qx is the same as the norm of x. So when you multiply by an orthogonal matrix, it's length preserving. So multiplying by q performs what are called like rigid motions, like rotation, reflection, things that do not affect length. So that's going to be very important to us for least squares problem. So that's q. R, and by extension R1, upper triangular. So that's going to be quite helpful to us also. I can also say R1, which is n by n, that is an invertible matrix. And the reason why is because we're assuming that the columns of A are linearly independent, therefore so are the columns of R1. Okay. Because really, all we're doing is we're linearly combining the columns of A to get the columns of Q1 there. Okay. Now, how does this help us with the least squares problem? So look at b minus ax, 2 norm squared. I can multiply this by an orthogonal matrix. Now, Q, I said Q is orthogonal, but if a matrix is orthogonal, its transpose is also orthogonal. So I can just stick that in there, and even though the vector inside will be different, its magnitude will be the same. Now, A is equal to QR, so if I multiply both sides by Q transpose, then Q transpose A is equal to R, again, using the fact that Q is an orthogonal matrix. I basically just multiplying by, well, Q transpose is Q inverse. So that gives me Q transpose B minus R X. Now, I'm going to replace R with how I decomposed it earlier. Also, Q transpose B, that's a vector. I'm going to break it into 2 pieces, C and D. So, okay, I need to explain the breakdown. C is the first n components, and then everything else goes into D. Because it's a M vector. And then here I have R1 up top, 0 down below, and then I have X. Okay. Now, when I take a 2 norm squared, so one nice property is, if I have a vector that's broken into 2 pieces, like Z is broken down into X and Y, or like stacked on top of each other, I can say that the 2 norm of Z squared is the same as the 2 norm of X squared plus the 2 norm of Y squared. And the reason for that is, this is the sum of squares of all of Z's components. Here are sum of squares of some of the components, and here's the sum of squares of the rest of them. I'm just breaking that up into 2 pieces. So I can do that over here, because I have the same kind of decomposition. So I have C, everything in the top half, C minus R1X, 2 norm squared, plus everything else, which is just D. So now, I've started with what I want to minimize, and I've gotten it to this. Now, how does that help me? Well, R1 is a square invertible matrix. So what I can do is solve R1 times X is equal to C. So I can make this part 0. This part is fixed. Notice it doesn't depend on X at all. I can't do anything about that. So that is the minimum of norm of B minus AX squared. So now, solving that system, R1X is equal to C. Can anyone tell me what method I can use to most easily solve that? Keep in mind, it's written on the board, what kind of matrix R1 is, which is written on the board there. So we can use
Gaussian elimination, back substitution.
back substitution. Yeah. All right, so apologize for my terrible board use. Oh. If I did that to move a computer, I might. Okay, so we can just use back substitution, solve that in order n squared operations, and we're done. So that is approach 2 to solving the full rank least squares problem. We compute the Qr factorization of A, and then we get this upper triangular system to solve. Now, as far as algorithmic complexity, there's no real advantage of one over the other because we have to, for normal equations, we have to form A transpose A, which takes order, we'll see, it's going to be order mn squared operations. So if n was equal to n, it'd be cubic. And then solving the normal equations themselves take order n cubed operations. So it's a cubic process. For Qr factorization, I've yet to tell you how we even get it, because that's Wednesday. I'm actually going to spend 3 class periods talking about how to compute the Qr factorization because of 3 different approaches. But whatever approach you use, that also is a cubic process. So solving any system linear equations, we're talking order n cubed work for a general case, unless you have some nice structure or sparsity to take advantage of. So there's no free lunch there. But at least because we're not computing, we're not multiplying matrices together, we're not squaring the condition number in this case. So Qr factorization is generally a more numerically stable approach. I wouldn't say it's universally true, but it is generally the preferred method of solving a full rank least squares problem. You just have to go to the trouble of computing Qr factorization, which is a challenge in itself. So the way they would teach you to do that actually they wouldn't even cover it in a first linear algebra course, maybe a second one, which we haven't offered lately. And you probably wouldn't even call it Qr factorization. If any of you have seen the Graham-Schmidt orthogonalization process in any class? What? What?
There were no processes in my linear 2 class.
Okay. Well, Graham-Schmidt orthogonalization is how they normally teach how to do this in some sort of linear algebra class. But that's actually the worst way. So I will cover it, but there are better ways. Yes?
So, to be clear, the first thing you have to do you get that, you don't have to do all that. Those are the normal equations. And then to solve that, your 2 methods are Cholesky or the QR.
No. Okay, so approach 1 is, normal equations, Cholesky, or QR. So QR itself is not separate from normal equations. Yeah. Okay. So I should have mentioned, so Qr factorization is not an alternative way to solve normal equations. It's an alternative way to solve the full rank least squares problem. Yeah. Okay. That gets you out of something terribly sensitive like the normal equations. So what I'm going to do during for next rest of this week and into next week is, well, A, take homework questions, That's one priority. And then showing you the various ways of computing Qr Factorization, which actually will help us with other problems later on in the semester, like eigenvalue problems. So you're going to learn some essential tools that are useful not just for least squares. Okay, so see what progress you can make on homework 1, and I'll be able to take some time on Wednesday to talk about it if you need to. Alrighty.